Oh. Sine.
Hello everyone, welcome to my channel, and we have 4 projects here. These are all previous projects, and let us see my previous projects. We have this one, this one, and this. I'm using an iPhone 4, and to explain the circuit we need a circuit diagram. So let us see the circuit diagram of each circuit. This is the first previous project, transformer pulsating LED module. That is the first previous project, and as you can see this here, LED is pulsating or blinking. That is our first previous project, and I'm using iPhone 4 to shoot this video, and you can see the blinking pattern of the LED. Let us see the circuit diagram to check why is it that the LED is blinking. Let us see that. So this is the circuit diagram. I have the transformer. So before that, let me get the pencil. Where is my pencil? Okay. Let us now see the circuit. We have the transformer, a step down, and then to the secondary I'm using a 12 volts, and this is a center type transformer, and to the secondary windings of the transformer I connected the resistor and the LED. And because I directly connected the resistor and the LED to the secondary windings of the transformer, the result is a blinking LED. That makes this project a title of Transformer Pulsating LED Module. You can connect the LED in series with the resistor directly to the secondary of the transformer. This is a step-down transformer. Also, I made some experiment here. The experiment. I connected lots of LED with no resistor to the secondary. And you can see that below in my video description below. So that is the current diagram, and I have the layout, also the parts, the actual module type, and that is the first project, first free use project. Let us now see the second previous project, and this one is the second previous project. Let us now check the LED. As you can see here, LED is blinking. I'm using iPhone 4 to shoot this video, and you can see that LED is blinking. Let us now see why is it blinking by checking the circuit diagram. This is now the circuit diagram of the second previous circuit. This is a transformer 1N4007 circuit. That is the name of the previous project. So in this project, we have also a transformer. Forget this. Let's talk about transformer. We have the transformer step down. Okay, step down. And instead of just connecting the LED and the resistor directly to the secondary, we add a diode 1N4007. And that makes the LED to blink. Still blinking LED. And I explained the waveform of the circuit. Also, I have the actual layout. You can see this in my video description below. You can check the video for this previous project. So you can see when you connect another diode here in series with the LED. Of course, we need the resistor here to limit the current flows at the LED. Still, LED is blinking. That is now our second previous project. And then I have also this. Let us see that. Something wrong with the camera. Okay. Let us check the lights of the LED. LED now is lighting and it is not blinking. I'm using again the iPhone 4 camera, and you can see steady lights of the LED. You can see here. So let us check the circuit diagram. The third previous project is this. This is a what is this? A half-wave rectifier. That is the layout. And this is the circuit diagram of the third previous project. We also have the transformer. Secondary, I'm using a multiple output transformer, but we're going to use the 12 volts terminal, 0 to 12. And then instead of just adding the diode, I add another component, and that is the capacitor. I'm using capacitor here, and then the load, and this is the load. So again, I'm adding a new component, and I discuss here. You can see this project in my video description below. You can see this project in my video description below. So I discuss all the waveforms here. What is the behavior of the circuit? You can see that the light of the LED is not blinking. It's steady because of adding the capacitor to the circuit, making this LED not to blink, or making the LED to not to blink, making this a steady light for the LED because of the introduction of the capacitor to the circuit. That makes the light of LED not to blink. And that is our third project. I also constructed another project, and this is another project. Let us check. It seems that the LED is nice and steady. It's not blinking. So let us now see the circuit diagram. For the fourth project, I have this. This is now the fourth project. This is a full wave rectifier center top circuit. Also, we have the transformer. I'm using a center top transformer to the secondary, this 0-12 volts. And then I use 2 diodes here instead of just 1 diode. And the capacitor, and also the load resistor and the LED. And that makes the LED to light steadily or not to blink. LED is now not blinking. LED is not blinking because of the construction of the project. 2 diodes. This full wave rectifier center top. And I discussed the waveform, the behavior of the circuit, the layout, and this is my previous project. You can check the video description below with this title. So we got a 4 previous project, and that is the behavior of the blinking pattern or the light of the LED. The 2 are blinking, the 2 are not blinking. We can now take a summary, or we can discuss the current flows of each circuit. Okay, we have now here the circuit diagram of our previous projects. This is the first project circuit diagram, and we're going to discuss the electron flow of the circuit of the first project, transformer pulsating LED module. What makes this LED to blink? So let us now examine the current flows. This is 220, primary side of the transformer, 220 volts, and then step down transformer becomes 12 volts. This is now the secondary windings, from 220 to 12 volts. A big sine wave become a smaller sine wave. This 12 volts small sine wave, it has 2 components. The first half cycle, second half cycle, positive half cycle, negative half cycle. During the positive half cycle, this is positive and this another terminal is negative. So this is small sine wave, which is 12 volts, will travel into the resistor and to the LED and go back to the other terminal, to the next terminal. So we got the complete circuit. Because of that positive half cycle, it has an output, this one. So if this is the input, the output is just the half. Input, output. Input, output. Since this is alternating current produced by the secondary windings of the transformer, this is still AC. During the negative half cycle, or the reversal of the wave, because the wave is traveling from forward and then reverse, negative, the other half cycle, the negative part, the polarity of the transformer will now become positive here and negative here. So the current now flows into the opposite direction. Since this is a diode LED, there's no output. It is reverse bias. So the output is this, flat. From positive, negative half cycle, flat. That makes the LED to blink. Because when we're going to use the 2 cycles, 1 cycle per second, 2 Hertz, 1 cycle, 2 cycles, this is the output waveform. We have a pulsating DC current. This is pulsating DC. During the first half cycle, we have the output. The negative half cycle, we don't have the output. Another half cycle, and the negative half cycle, no output, because we're using 2 Hertz here in this example. Here, only 1 Hertz. 1 cycle per second. So, as you can have seen in the waveform, that makes the LED to blink on and off. On, off, on, off. You can see that in our demo. What is the disadvantage of connecting the LED to the secondary windings of the transformer? Because of the low intrinsic value of PIB of this LED. What do I mean by this PIB? Peak inverse voltage. Because during the reversal of the wave, the negative half cycle, current travels here, and then what happened to the LED is it is reverse bias. How long will it take to counter the reverse biasing of this diode, the current, or the current source, or the current that flows here? How long will it last? It is not advisable. It has a low PIB. It will burn out the diode, the LED, when you're using it in the long term. That is the disadvantage of this circuit. But still, you can connect this for at least a short period of time, but not for a very long time, because the wave is traveling alternate from here and here. Half cycle travels here, the other half cycle travels there, and there comes a time this will burn out because of the low intrinsic value of PIB. So we have a special type of diode we can use to protect the LED, and that's why I constructed another circuit. And before that, because of this transformer pulsating LED module, we know that the LED is pulsating or blinking. What kind of circuit we are already constructed? We constructed what now? What type? This is half wave rectifier, but it is unadvisable half wave rectifier, inefficient. Did you see the wave here? That's the wave rectifier, pulsating DC. But the peak and burst voltage value of this LED is very low. It cannot protect itself from burning for a longer period of time of using. So I decided to make another circuit, and we have now another circuit, and that is in figure 2, transformer 1N4007 circuit. So in this circuit, we have also the transformer, the secondary, primary, a big sine wave, 220 volts becomes 12 volts again. The big sine wave becomes the small sine wave here. Still in the secondary, it is 12 volts AC. This one. So again, during the positive half cycle, as I've said, what's the difference? Why did I construct this second project? Is because the difference is I connected a new component here, and that is 1N4007 1 ampere. That is the current rating it can handle, 1 ampere. This diode now, 1N4007, will help to protect the LED from burning, or due to the peak and burst voltage or the reversal direction of the wave. So let us now examine the current flows. So we have now the current here, positive to negative, positive, negative during the positive half cycle. Current now flows into the diode, forward bias from anode to cathode, and then to the load and back to the other terminal. And we have now the waveform output. From this becomes this positive half cycle. Since this is alternating current, still the 12 volts, during the reverse of direction of the current, this now become positive and this become negative. Current now travels here. That is the conventional current flow from positive to the load, and it will not close here because this is reverse bias. The same time, the diode 2 or 1N4007 is reverse bias. So again, during the negative half cycle, it has no output. See, from with output, no output. Again, this is a pulsating DC. What's the difference with the two? It is much durable or flexible or efficient, because we have now a diode that can protect the LED from burning due to the reversal direction of the wave. The peak and burst voltage of this diode is repetitive voltage according to data sheet of almost 1000 volts, up to 1000 volts. It has current rating of 1 ampere. That is the current it can handle, 1 ampere. And our transformer, I think we got only 200 milliampere, so it's safe. That is the use of diode in the circuit. And this is the modification of this. Just connect a diode in series with the load, with the LED, and it will protect the LED from burning due to the reversal or the reverse bias condition of the LED. It will not break or burn out due to the high PIB rating of the diode. That will serve as the protector to the circuit. Using 2 cycle, same. What we have, the pulsating DC, still pulsating DC. With output, with output, without output, that is pulsating DC. And that is now the advantage of connecting a diode 1N4007 to the circuit in series with the load. This is our load. Serve as protector to the peak reverse current source. During the reverse bias condition of the diode, it will not break the barrier of the cathode. And that is now our second project. Let us now see the other one. This one. Let's okay, we have now another third project. So, as you have seen in the previous, here the LED also blinks. Remember? Here LED blinks also here. But here, let us see. What makes this LED not to blink? Now, we have another third project or another previous project, which is the power supply half-wave rectifier detachable. That is the video title. Only a video title. In here, instead of connecting a diode only, I connect another component, which is the capacitor, equivalent to 3000 microfarad, 25 volts. What is the use of this capacitor? It helps to filter out or to filter the wave. Again, the same operation. During the positive half cycle, current travels to the diode, charging the capacitor into the other terminal. Negative half cycle, positive here, negative. Now, the same. It will not travel here. What happened is, now the capacitor is charging. At this state, it will discharge to the load. This is now the one who is supplying the load current, or the one supplying the current to the load, the capacitor. The discharging effect of the capacitor, it supplies the current to the load. That make this wave filtering the wave. Instead of just pulsating, it will filter out. This gap, big gap, become like this, becomes a filter capacitor. And now this is the what they call a ripple voltage. We got a ripple voltage here. The bigger the capacitor, the smaller the ripple voltage. So that is the operation of the half-wave rectifier. During the half cycle, still the same. It conducts. The other half cycle, it will not conduct. The difference is we're introducing a capacitor that filtering the waveform. Instead of just like this, it becomes like this. See? Okay, we have another circuit. This is now another circuit, full wave rectifier center top circuit, which is the modification of this half wave. We're now going to utilize the use of a full wave. That's what they call it, a full wave rectifier. We're going to rectify a signal without with a good efficiency. So again, I have the two diodes here. That is the construction. I'm using the center tap transformer, the capacitor, and the load. The other end is the diode. The other end is the diode. During the first half cycle, positive here. Current travels to the T2, charging the capacitor, and to the ground. The ground is the center tap of the transformer. During the negative half cycle, again, since this is positive half cycle, it has an output of this, a parabolic type of graph. and then to the negative, reversal of the wave, negative here, positive here. Now the D3 is now functioning. Current travels to D3, to the capacitor, and to the ground. So in one cycle, we are now having this, a nice pulsating DC. Much better than the half wave. Because the half wave, there's no output to the negative half cycle. Here we have. So what happened is, again, the capacitor is charging. And it will discharge like this to the load. And we have now a nice ripple voltage here. We are using 2 cycles. This is now the waveform. So you can see here, during the half cycle, this D2 conducts, current travels, and this is reverse bias. So current travels to the capacitor and to the center top. And then to the negative, reversal of the wave, reverse current. Now the current now flows into the other end, to the D3. Now this is now reverse bias. And charging the capacitor. This is now the one supplying the current to the load. This filtered. And because of that, our LED is not flickering or not blinking. Here, also not blinking because of the capacitor. But here also, the LED is not blinking because of the capacitor and the very nice construction of the full wave. You can see here, the diode are working utilizing the full wave. That is the brief summary explanation of this full wave rectifier. But the efficiency of this is not quite efficient. I think 40%. So there is another invention, a type of rectifier. So all in all, these 4 circuits are all rectifier. What do I mean by rectifier is it converts the alternating current into direct current. The direction of the current alternates, now becomes only in one direction, that flows in only one direction. That is the purpose of rectifier, converting the alternating current AC to DC. But still, this is not a pure DC, this is pulsating DC. So we now come to the another type of rectifier, which is the full bridge rectifier. And let us see if what is the circuit diagram, and that is now our new project, designing a full wave rectifier.